Hello. In today's lecture, we will be discussing the kinetic models we use to explain the dynamics of the outbreaks, epidemics, and we will try to expand our examples in this type of models. Just a quick reminder, how did we model the progress of an epidemic? We divided the population into three subgroups we called compartments: the susceptible group, the infected group, and the recovered group, and assumed that each group has a certain number of individuals for a time being. Then there are rules defining the people leaving one group and entering the other group. And we represent these rules as some differential equations. Differential equations mean equations which have derivatives, rate of change for the number of people in certain compartment. For example, for the rule that defines the people leaving the compartment S and going into the compartment I, the rate of this movement is proportional to the number of people in S, but also the number of people in I, times a factor which is constant. Alpha is a constant. But even if the alpha is constant, as S and I will change due to this movement, the derivative ds over dt, the rate of movement from S to I, is not a constant. It will change as S and I changes. This and also you define similar rules for other compartments. For example, for the I, the change is not dependent only on S and I and alpha, but also it all depends on another factor, beta, and beta determines the rate of change or rate of flow out of I, and alpha, S and I defines the rate of flow into the I. So you take the difference between these two flow rates and find the final rate of change, or the real total rate of change of the I, population I, so on and so forth. So this is how we define the model, while trying to explain the dynamics of an epidemic as it progresses. However, we can use the same type of thinking to understand other stuff, like the distribution of a drug in the body. For example, we can think about the body made of different compartments, and the drug enters the body through one of the compartments and goes from one compartment to the other, and then from that one to the other one, and leaves the body. For example, here you take the pill, you swallow the pill, it goes into the gastrointestinal system. From there it goes into blood, and from blood to kidneys, and it's excreted in the urine, which is the way the drug leaves the body. So, what will be the concentration changes in these compartments after you take the medicine or the drug? You can use exactly the same model which we use to explain the dynamic of the epidemic, the SIR model, and relabel the compartments. But in a sense, the model is essentially the same, because the movement from one compartment of the drug, the movement of the drug from one compartment to the other, is essentially one way. It goes from gastrointestinal system to blood, and from blood to urine, but it doesn't come back from urine to blood. or from blood to gastrointestinal system back again. Because of this, we can apply exactly the same model we used for the epidemics, the SIR model. And we exactly use the same mathematical expressions to define the movement of the drug from one compartment to the other. Because we will see the reasons for that, but these are realistic equations to explain the movement of drug from for example, from gastrointestinal system to blood and things like that. However, it can be different than this. For example, you can add a fourth compartment, which, for example, the central nervous system compartment, which is not the same thing with the blood compartment, because there is a thing called blood-brain barrier, which restricts the movement of chemical substances from blood to central nervous system. So it can be seen as a different compartment, the central nervous system. And of course, there can be two-way movement from blood to central nervous system and from central nervous system back to blood. Then you have to define that too and add the appropriate differential equations to explain that type of behavior. So here, for this type of model, the movement is one way, always from one compartment to the other, but never back to the original compartment. The amount of the drug in these compartments are not expressed as the amount of drug, like milligrams or grams or moles, but in terms of concentrations, molar. So the concentration, the sum of the concentrations are not constant, but the sum of the amount of the drug in each compartment is constant. So when we say the S plus K plus U is constant, we don't mean the concentrations. These are simply the amount of the drug. You have to multiply the concentration of the drug in that compartment with the volume of that compartment. Then when you add them up, they're constant, because the drug is neither created nor destroyed in this model. It goes from one compartment to the other. As an example, we can give another kinetic phenomena which has to be modeled in a two-way movement. Binding kinetics. What do we mean by binding kinetics? If you remember your chemistry lessons, if a substance A binds to a substance B and they form a complex AB, which can break up into A and B back, which is a reversible reaction as shown in the figure, then what you will see is, if you start with a certain amount of B but a different concentration of A, each time you will the concentration of the A-B complex will change by time, and it will come and equilibrate or stop at a certain concentration as shown by the graphic. So the initial concentration of A is A0, and you have four different concentrations that you start with. The initial concentration of B is the same, but the initial concentration of A is different, and they're shown as A01, A02, A04, 3, and 4, because those represent the different concentrations, the initial concentrations of A. Chemistry class, we usually discuss about these endpoints here, which are called the equilibrium points. So this formula shows us the equilibrium point of each reaction, where it will end. However, the kinetic of it, the time course of that change, is different. What we usually show is represented in this graph by the red dots is these equilibrium points shown by the arrows, not the kinetics of it. So you have to be careful. The graphic on the top is a time, shows the time dependent change of a concentration of the AB complex. The graphic in the below shows the equilibrium points for the initial A0 concentration and resulting equilibrium point for the AB complex, concentration of the AB complex. How to approach the kinetics of it, the time course of it. So you have to divide the chemical reaction into two compartments. One compartment contains the free A and free B. A plus B is shown here. And the other compartment contains the complex. The concentrations in these compartments will change by time, and there are two-way movement between these compartments. You can move from AB, free AB compartment to AB complex compartment, and vice versa, from AB complex to the free compartment. Shown by blue one, red arrows, two arrows. And there are two constants which determines the movement from one compartment to the other. They don't have to be equal. They can be different here. So there are two differential equations, of course, to define the movement of the substance from one compartment to the other. One is the movement from the free compartment to the bound compartment, or the complex compartment, AB compartment, from left to right, the blue arrow. And the equation is that the rate of change in the complex, because the blue arrow is towards that complex, it will increase the concentration of AB. When the substance moves from free compartment to the complex AB complex compartment, the concentration of AB will increase. So it is a positive change, rate of change. The AB over dt is a positive number, is equal to the concentration of B, concentration of A, the free A and the free B substance, times a constant, which constant means constant for this reaction. It's not a universal constant. For a certain A and a certain B to define compounds, and for a defined temperature and pH and things like that, it's a constant. It does not change by the concentration of A and B. Okay. So the AB concentration, the concentration of the change, rate of change of concentration of AB is dependent on the concentration of free A, the concentration of free B, and this K1 constant. This is so because for this reaction to happen, A and B has to encounter each other. And the chance of encountering, or the rate of encountering, is dependent on how large the concentration of A and B is. And that K1 constant actually is related to the chance of each encounter ending up with a chemical bonding. It's very much like the encounter model, or the encounter scenario we talked about in the outbreak model. The sick and the susceptible individuals have the encounter, and each encounter has a probability of disease transmission. It's very similar here. And when you look at the red arrow, the AB complex also degrades into free A and free B, because it's a reversible chemical reaction. And the rate of movement from complex to free form is directly proportional to the concentration of AB times the K2 constant. K2 constant is the probability of one AB complex to disintegrate for a given amount of time. So the derivative is negative because this path from shown with the red arrow, is taking stuff from the AB complex away from that compartment into the free compartment. So it decreases the concentration of AB. It has to be a negative derivative. Okay, so then you have to take into account both these reactions because the sum of these rates is actually the net rate of change in the AB complex concentration. However, when you assume that there are no coming back from the free form, you can say that when the A and B complex disintegrates into free form, you wash them away instantly, or they dilute into a very large volume. Then they practically have the concentration of A and B 0. Then you end up with, in the simplified form, you end up with a reaction like this. And of course, the derivative, the differential equation is becomes simplified. What is the time course of this? What is the change in AB concentration with time? You start with a certain concentration of AB, and how it changes. It will decrease, but what will be the form of this decrease? What kind of a function it will give us? First of all, if you think of it, if the probability of an AB complex to disintegrate in a given period of time, let's call it a step, is 1/3, 0.33, something like that. And then what it means that the next step, you'll end up with the 1/3 of the AB molecules disintegrated into A and B, free A and B. If they are washed away or diluted into infinite volume, then what you will end up with is this AB molecules, only the 2/3 of the original. Then now the next step, 1/3 of the leftover ABs will disintegrate. Because this probability, it's a constant probability. It does not depend on the concentration of AB. Each AB complex has its independent probability of disintegration. So as you can see, what we are doing here is dividing each step with a constant. The equation also tells us that the rate of change, which must be negative because the A and AB complex will decrease, so derivative has to be a negative value, which means that each step, the number of molecules that will disintegrate is proportional to the amount of AB complex, directly proportional to that, which means that as division is a subtraction, actually, you have to subtract a certain amount of molecules from the number of given AB molecules at each step. And the number of molecules that you subtract is proportional to the number of the molecules at that step, which is basically saying that we divide the number of molecules at each step by a constant number. As you remember, this is a geometric series, a decreasing geometric series. And of course, a geometric series is related to, very intimately, to exponential functions. So this is a decreasing exponential function. You can see it from this equation also. The derivative of AB, or the dAB over dt, is equal to the AB. The function that relates the concentration of the AB complex to time. The derivative of this function is itself times a constant. This is this tells us that the AB, the function that relates the concentration of AB complex to time, is an exponential function which has a negative constant multiplied by t, because it has to be a decreasing function. It's not an increasing exponential function. Okay, so if you take one part of the one arm of the this reversible binding reaction, then you'll end up with a decreasing exponential function. Let's take another example, diffusion. Then we have to have the take into account both movement in both directions. What's happening is, you know that the concentration difference causes a net movement of substance from one compartment to the other. Here A has a large concentration on the left-hand side compartment. Then there will be a net movement towards the right-hand side, and then the concentration will become equal. The concentration will decrease in one and increase in the other, and when the concentrations become equal, the moment will end. So when you look at the molecular level, what's going on is that the movement from one compartment to the other is due to the molecules that are close to the interface. Okay, so let's talk in simplified terms. This is not exactly true, but to give you the idea, I'll give you a simplified version of the picture. Each molecule has a equal chance of moving to the right or to the left. If it moves to the right, it will go to the other side. If it moves to the left, it won't go to the other side. So each molecule on the border has equal chance of going to the right or to the left. So half of the molecules, approximately, will move towards the other compartment. The other half, they won't go to the other compartment. So basically, this is why you get a flux from one compartment to the other, which is the size of the flux, the derivative of change in the concentration, which must be negative in this model, because the molecules can only move out of this compartment, shown by the blue arrows, in a single given period of time, a short period of time. The number of molecules that will leave this compartment is proportional to the number of the molecules in that compartment, which is concentration basically, if this volume is a unit volume. And in every part of the compartment the situation is the same, then it must be proportional to the concentration of molecules in that compartment. So it's the same for the other compartment. So half of them will go the other way, but half of them will try to leave the right-hand side compartment. And again, the number of molecules that will leave that compartment will be proportional to the concentration in that compartment. So as you can see, as these moments are completely by chance, random, the number of molecules going from left to right is naturally higher than number of molecules going from right to left, because there are more molecules on the left hand side. So this will end up with a net movement from left to right, but not from right to left. But there are molecules coming from right to left, as well as molecules coming from left to right, but the number of coming from left to right is larger than coming the other way, the molecules that are coming other way. So you can see that then you can write the differential equations here, and you have to take into account both movements, because if you take into account only from left to right, then you overestimate the movement, because some molecules are coming back into the not back, but coming from right to left, so the net movement is less than what you will find when you take only the movement from left to right. But again, then you have rate of change in the concentration, which is proportional to the concentration in that in that compartment, and one movement will be larger than the other if there are equal number of molecules on each compartment. Then the number of moving particles from one compartment to the other will be equal, so the net movement will be zero. If the number of particles on one compartment is, for example, the one on the right is larger than the left, then the net movement will be from right to left. So as the movement occurs, the concentrations in the compartments will change, so the derivatives will change, so the net derivative will change. This is the kinetics of the diffusion. You'll end up with. Okay, so this is a general explanation or a general introduction to kinetic models to understand different types of phenomena. However, they use the same logic and the same mathematics. See you in the next lecture.